Hi there, you're welcome back to my channel, and in this video I'm going to take you through maximum value for directional derivatives. The maximum value for directional derivatives. So I have a theorem here. It says the maximum value of any directional derivative is given by what? The absolute of what? The partial derivatives at that particular point, okay? And it will occur in the direction given by that same particular point at the partial derivative. We have a proof for this, but before that, if this is the first time you've been on this channel, kindly subscribe to support and please watch this video to the end so you understand every part of the video. So let's see. In our previous lessons, I taught you about directional derivatives. That directional derivative is simply the dot product of the partial derivative of a function because you are in the multivariable function by its unit vector. Okay, its unit vector. So you simply multiply the directional numbers of the unit vector with, the corresponding components of the partial derivative. So the first x part of the unit vector or multiply the partial derivative with respect to x. Likewise, the b will multiply the partial derivative with respect to y. So in this case, to prove the maximum value for directional derivatives, you know that a unit vector can be represented as an angle theta, right? And angle is the angle will be between our vector and our directional derivatives. So for a maximum value, the angle will be theta will be 0. So at theta equals 0, that's when you get the maximum value of our function. Because if you have a vector, let's say AB, right, multiplying f of xy, where a and b are cosine of angle theta, and b is equal to sine of an angle theta. Cosine and this sign here, for us to attain the maximum directional derivative, whatever we are multiplying by our directional derivative should be 1, right? It should be 1, and it will occur only when the theta is equal to 0. So at that time we get the maximum, right? So once you do that, our unit vector simply becomes 1, and our maximum value becomes the absolute of the directional derivatives. So I have a problem here for us to solve so that you understand the maximum value for directional derivatives very well. So the problem says that suppose that the height of a hill above sea level is given by z is equal to 1000 minus 0.01 s squared minus 0.02 y squared. If you are at the point 60, 100, right, in what direction is the elevation changing fastest? What is the maximum rate of change of the elevation at this point? So this is a problem which I'm going to take you through so that you understand directional derivatives very well. So at this point, let's write our function here. So z is equal to 1000 minus 0.01 x squared minus 0.02 y squared, right? Then at the point 60, 100, right? So once we've been asked to find the direction where the elevation is changing fastest, so the key word here is the fastest. So meaning we are looking out for the maximum directional derivatives, right? So this is a scenario where the function is changing. So the height of the hill is given at this function, okay, but it has the partial derivatives gives how the function is changing with respect to x and y. And also the concept of directional derivative is when both x and y are changing simultaneously. Remember that a partial derivative is when the x is changing with respect to x alone, but for directional derivative we take into consideration both x and y changing simultaneously, right? So they are asking us at what point will our function change at the maxi, right? So we want a maximum change of our function, right? So now the first thing to do is you need your partial derivatives. Okay, you need your partial derivatives. But before that, I said whenever you want to start directional derivatives, look out for your vector and as well as the unit vector. But in this case, the keyword fastest here tells us that our unit vector is simply giving us 1, 1. Okay, like everything is 1. It has the length of 1. Sorry, it's not necessarily 1, 1, but our unit vector simply is 1. Okay, so we don't need the unit vector in this sense. So whenever they say that find the maximum value we don't need a unit vector. We are only interested in our partial derivative because it's assumed that the unit vector here, or there will be a maximum change provided the unit vector yield a result of what? 1, right? If it doesn't yield 1, or if the angle is less than, or if the angle is not 0, then you'll be getting maybe cosine of what? Maybe let's say 30, 40. That will reduce, or that will, reduce the yield of what? Our change, right? Because it will be a fraction, so it will be a part of it, or a fraction of it. But if you want a maximum, then it should be what? 1, so that you just get completely the change in what? Our function. So let's see, let's find the partial derivatives. So we need zx. What is zx? 1000 will be 0, and I'll have negative 0.02x. This part will be 0 because we are differentiating with respect to x. Okay, then we need zy. Our zy is giving us, this will be 0, x part will be 0. I'll have negative 0.04y, right? So once you have zy and zx, remember that we were asked to find the change at a particular point. Okay, so to find our maximum directional derivative, is giving us the directional derivative at the point 60, 100. As simple as that. At the point 60, 100. So I'll just put 60 here, then I'll put 100 here. So this is equal to, I'll bring my zx, which is negative 0.02, then I'll multiply it by what? 60, right? Then my y2 will come, which is negative 0.04 multiplied by 100, right? So what am I getting? I'm getting negative 1.2 comma what? Negative 4, right? So once you get this, remember that the maximum value, as I said, is the absolute of what? Our directional derivative. So f 60 comma 100, right? So to find the absolute of this, you're going to get square root of what? Negative 1.2 all squared plus square root of negative 4 all squared. And this is giving us the square root of 17.44, which is also equal to 4.176. So this happens to be the directional derivative of our rate of change from the elevation, but is the maximum directional derivative. So you should take note that whenever you do directional derivative, you should end up getting a scalar because it's the dot product of the unit vector as well as what? Our partial derivatives. So now our maximum directional derivative is simply what? The absolute of what? Our partial derivative at that particular point. Now the question went ahead to say that what will be the direction of what? The rate of change. So from the theorem, it says, the term says, and it will occur in the direction given by what? Our partial derivative. So as simple as that. So for that reason, our direction will be giving us, the direction will be giving us what? Negative 1.2 and negative 4, right? So meaning that to change by 1.2 units in the x-axis or in the x component, and it will change by negative 4 in the y. Thank you for being with me in this video. This is the end of this lecture. Kindly subscribe, you like, and you share.